something. Time. What can be positive today? Yes. Pilot wire protection. What can we do about power lines? Current, difference of current, if great, we should send disconnect signal. Very easy drawing. But there is one tiny problem. I need to get these two currents together. If I would try to organize simple 5-amp current circulation for tens and tens and tens of kilometers, I should build a communication infrastructure more expensive than the line itself because of huge losses. I should be able to get this information together in some kind of economic, reasonable manner. Here, problem number one is communication. And in historical in historical view, first solution was to use a simple form ground communication infrastructure. And ground communication lines are for a rated voltage of 60 volts. Oh, really successful design was like this. First, to reduce amount of circulating information, special technique of so-called proportional valleys was used. Idea was not to compare currents itself. Currents were subjected to symmetrical component-based transformation. It was direct current plus factor of negative sequence current. Direct sequence current plus factor of negative sequence current. Zero sequence was excluded to prevent false operation of outer faults and to reduce influence of line on balance. Actually, for most fault, only negative sequence would be sufficient. But to get this system operational in case of three-phase fault, also direct sequence was used. Factor was used something like 1.5 and something like this. The dominance of negative sequence. Proportional value to reduce amount of transferable information, but that's not all. Switch to proportional values or derived values of proportional values allow to reduce influence from outside and from reduced influence from parallel line. It's also kind of problem because when we have two lines and form here through coupling, we have an influence what can cause enduring separation. Because this coupling moves in zero sequence, elimination of zero sequence increase robustness or safety of operation of such system. Okay, it's a moment one. Next, what to do with this proportional value? We need to organize kind of data exchange, synchronous data exchange. The first solution, really working solution, was like this. Values from proportional field were supplied to specific kind of transformer. Gas discharge of wall limiter, or sometimes they call surge arrestor. This gas discharge limiter gas discharge limiter something like this. Secondary voltage. Introduce characteristic like this, limiting. On the one hand, it protects line with the limited voltage capability. And also introduce non-linearity in the system. This helps to reduce probability of false operation. Okay, next one. Now I need to interconnect this. And here is very smart example of very smart design. Two rectifiers are installed on each side of the line. One rectifier bridge and second rectifier bridge. From the first, and the special balancing current relay used. Relays with two balancing relay with two coils. One, to say forward, where is my balancing? Okay. Oh. Come here. Two coil relay with coil to switch and coil to not to switch. Such kind of design. Or differential relay. Two coil relay. Special differential relay, one coil. Yeah, is a power for coil number one. Coil number two also needs a filter condenser. Now, this goes here. And outside. Signal from transformer this should go forward. To very the opposite side, and this one is powered by its rectifier, but it's simple. I will show it as E. It's a line control system's power source. On the opposite side is the same, excluding one thing. On the opposite side sits blocking relay. How this thing works? Oops. How this thing works? Idea is what proportional at each side. Here we have one force from that my side. So as you can see, it circulates through this bridge. This one is to stop. Next to this bridge and through the line is being sent to line. From the opposite side we get back transformer currents are equal, relay will remain stable. But if, for example, we have internal fault, if you will get internal fault, in case of internal fault, current here will be 1 unit of current. But through this coil will flow own current plus current from opposite side. And it will be 2 units. So relay will trip. In case of outer fault, here will be 1 current, and here different will be, if currents are equal, 0. Result will be 0. So, trip moment will be -1. In case of internal fault, -1. In case of external, -1. In case of internal, here, +2, here, -1, resulting 1. Relay trips, protection disconnect. On the opposite side is the same. So comparison is between own current lines sent from opposite side. This is because here with this side, you can in orange, it's an underground phone cable, 2 wires. This design gave us name pilot wire. This underground cable, it is pilot wire. So here we have model, what? On the opposite side, the same schematics. What we have here? 2 things. First, from real currents of line proportional value is derived, and second, date exchange, it's a date exchange, goes through current loop, this nice current loop, to prevent false operation. If this current loop is disturbed, first, our information circulates as 100 Hertz current. DC component here is a power supply and DC relay. DC components allows to check line integrity. Also, it had 2 relay insulation control relays, voltage relays, to check line insulation against ground. Also, later designs had integrity, sorry, not from ground, but from, it's better, it's DC source. Later designs had current relays in the supply line. Also, it's a check for integrity. Loop integrity check. kind of protection was very popular for high importance lines. It has a limited range because you need communication cable between under your line. Limited range, but appear around important power plants and interconnections between power plants. It's one of its child was so-called high frequency protection. Its derivative, which what I would like to say, it's based on a technique called power line carrier. We can use our power line as a data bearer, as a transfer medium. Idea is to plan it's approximately 100 kilohertz field. Oh, it should be switched somewhere. Plan these filters. This makes a line kind of isolated for 100 kilohertz. Frequencies were varying from lower end was somewhere around 50 kilohertz and upper somewhere around 300. Very popular, 110, 120, 95, something like this. Avoiding areas used not for civilian communication and naval communication. Here, with the help of capacitive divider, RF coupling can be created, and on this coupling sits both receiver equipment for 100 kilohertz and transmitter circuit on the both ends. RF coupling, receiver, transmitter. For transmitter circuit, manipulation schematic was quite simple. Proportional various field. Greater element. $100 approximate Block frequency oscillator. This enable and this manipulate. Resulting signal, if primary current is something like this, resulting signal will be in simple way set of high frequency bursts. Approximately 10 millisecond burst of 100 kilohertz signal. Here A, B, C current. And what? For example, internal fault and external fault. In case of internal fault, currents are oriented inwards. Because current transformers are oriented towards bus, our current will be like this. In opposite case, we will have I1 and same current, but with opposite sign. Transmitter 1 will set this kind of burst. Transmitter 2 on the opposite side will do the same. Here, transmitter 1 burst. Transmitter 2 burst, silence. At receiving end, it's an output from receiver. Output from receiver will be like this. Large signal when receiver hears own transmission. Here, receiver gets signal from own transmitter. And smaller signal, receiver hears remote end. On, remote. On, remote. In theory, if angle between systems is 0, we will see no interruption in signal on the output of transceiver. Sorry, what I'm drawing. 1 second. As I selected, what we will hear? 0 from remote. What I'm doing? I hear in this build, sorry, I'm hearing on plus remote, and 0 between them. Here I would hear, with this build up, I will hear 1, lesser, again, high. Yeah, sorry, I'm drawn wrong. This one is correct. So, here at the output of receiver, I will have burst 0, 1, 0, 1, 0, 1, 0. From this one, uninterrupted, if zero angle between them, or with in reality it can be transfer and some transfer angle. I will see small interruption. But idea, if I have 1, 0, 1, 0, 1, 0, here will be 1, 1, 1, 1, 1. With this gap, at last 6, 7 milliseconds, I should disconnect line. Actually, robust and reliable thing. Once again. Internal fault. Ohm. No. Remote. Internal fault, ohm plus remote, output 1, 0, 1. If this gap is above 6, 7 milliseconds, it's internal fault, we need to disconnect. If we get ohm, remote, here will be it's external fault. We will get something 1, 1, 1. External fault, no operation is needed. Or maybe in some transfer angle, small, boom, but it can be 2, 3 milliseconds. Not much. Good reliable protection. Worked well. But some problems first end of its life in our region. It's a maintenance problem. These transmitters, based on 606 or 870 electronic valves, become obsolete. No new models presented, and the nest of skilled radio engineers, necessary to get skilled radio engineers to maintain it. Now it's discontinued. Filters removed and equipment decommissioned. another version appeared in small quantities on market was with radio tower. Same thing, but instead of power line carrier, radio directed radio towers were used. Needed direct visibility, problem, incorrect frequency range selected. Equipment was for 450 megahertz and conflicted with small radio communications. First were police radios, then they appeared in civilian version 450 megahertz. And the mobile system, all decommissioned. No one of such protection left in service. What next? Of course, we go into digital era. Everything should be digital. And we have digital communication channels, so why not exchange data digitally? On a first glance, it's very simple. Take our current to analog to digital conversion. Analog to digital conversion. Of course, we need some processor to exchange our data. Modem. Data communication, data infrastructure, modem, exchange. Data exchange, we will have here our measurement point. So we will have current as a function of discrete time. From the one side, I2 as a function of discrete time on the secondary side. Only compare them face by face and you get everything you need. Yeah, of course, you will need stabilization chart inside your processor device. Because you need to do something with these transformer errors. So inside your processor logic, here will be I1 minus I2, I1 plus I2. Instant values. This stabilization chart needs to compensate an error of this transformer. Follow this characteristic and everything should be fine. No, it looks easy, but there is problem, multiple problems. The problem is I need to compare current values without time shift, they should correspond to one and same moment of time. Oh, that's a problem. You just measuring and synchronous. Problem is what this nice picture, modern communication structure. I do not own this line. And renting a dark fiber would be extremely expensive. To get my pilot via digital protection, measurement points at one side and measurement points on yeah, I'm on pilot via protections. So where we are? I'm on the one side and another side of my line. Here are measurements. For example, taken with step 1 millisecond, tau 1 millisecond. To operate safely, I need to compare measurements from one time moment. When I deal with communication infrastructure, it's not my own. It belongs to communication company, or even it's a branch of my power company. It's not my own. I'm only one of the users. I will get in early version synchronous interface like X21. In modern version, I will get Ethernet and TCP/IP from the TCP/IP gate, kind gate. To get it simple, I'm on a physical location 1, physical location 2. Data infrastructure. I will have end user attachment. I will have the Я вообще зачем студентам лет? Boss wants to see me. Problem, it's like data in between my device and cable is the modem and the data interface. For simplicity, it's like data, I don't know. Kind of data train going toward relatives in exchange of a TCP/IP. Locomotive. When I need to send this point, I want to send it. I will get first carriage available. Occupied, available. Train, this train, some megabits per second. This train goes, and with some delay, it's a so-called propagation delay, will bring my date to the opposite end. Then my device from other side need to send me this value. I've sent this value. It's arrived. Then I need to get back this value. Goes this way, goes backward. Where am I? If I compare simple, without thinking, it's possible what I will compare, for example, with this one. I need to, it's a shift caused by propagation delay. Because data needs to go this way and go back. If I own this communication cable, it's microsecond. But because I'm not owner and I need to wait for my carriage, and I need all data processing time, there will be some delay, maybe millisecond, maybe half millisecond, but it's always big. What can I do? First I need to remember it. I can try to compensate propagation delay. How? I can try to measure it. With a time stamp value. So here is time of device 1, time of device 2. Device 1 wants to establish a communication. Before sending any current, it sends a request. Say, how are you? But this request is time stamped. It also has this plus time 1. Device 2 responds, oh, I'm fine. It arrives at time 2. So propagation time should be T2 minus T1 divided by half. I need to shift current to correctly compare current. I need to do what? I have received this measurement. We do exchange data. Now we can exchange currents. This will be okay to send, and I will get current I2. I need to implement this delta T propagation shift. So this measurement should be shifted backwards to this time. From the opposite side, we do the same thing. Opposite side also measures this time difference and also estimates propagation time to shift red date. It's very nice, but the life isn't so easy for us. It's a problem called jitter. Data infrastructure, this communication network, do not offer me same carriage, same time slot any moment. I will get first available. Not the same one, but first available. They they guarantee that propagation time will be no higher than. But in reality, we have problem. When network load is at minimal level, at night time nothing happens. Okay, maybe some SCADA data exchange. This data train, carrying my data is completely empty, and I will get this carriage. Daytime, when I don't know, it's video, it's accounting office, I don't know. Occupied, I will get this one. There is a difference. Also, in reality, there is no constant propagation time. It's always changes. Something happened, I don't know, someone opens a web page, propagation time increases. Web page load, propagation time decreases. So-called jitter. Propagation time is a function of something random. What it leads to? It leads to problem. In theory, I can measure propagation time continuously. It's not a problem. Each packet will be timestamped. I will measure propagation time constantly. Problem with my measurements. I'm not taking 100 million measurements per second. With this gap of 1 millisecond, jitter causes me, creates a situation when data is untrustable. They always different. This random function of network load is much faster than current. And I am always swinging somewhere. I cannot trust synchronization data. This leads to a situation where protection device stands months, 2 months, 3 months, all showing propagation unstable, communication error, propagation unstable. Especially, it's a pain for TCP/IP network. They are, Ethernet is SMR CD based, nothing can be done. Excluding, what we can do? We can use outside timing source. Modern protection devices, pilot wire protection devices, do not rely on propagation time measurement. They check propagation time to avoid, to check data channel integrity. But they do not rely on the shift. Idea is more complex. How it's work? Inside device, it's a model of RTC, real-time clock. Each measurement, here are current measurements with the same 1 millisecond. Each measurement is pegged in frame. Time, EA, AB, and so on. Each measurement is time stamped. It comes with the time of RTC. And so on. Very nice. But how can I keep RTC in shape? Let's say 4 black wires. 2 in, 2 goes out. Come here. This small thing is a GPS antenna. It receives signal from global positioning system, from Navstar system. And then mushroom of the antenna receive signal called IRIG-B. It's a timing signal from Navstar system. RTC is synchronized with Navstar system, and from RTC, time for time stamping is taken. On the opposite side, same thing. So, model. From this side we will also get time stamp date. Time stamp with time synchronized with Navstar system. Now, how it's done now? Good news, it works very well until war knocks at the door and global positioning system is jammed. All these protections are equipped with fallback function. In case it is not possible to establish safe communication with date synchronicity, and in late version with encryption, they fall back to distance protection. If data synchro channel cannot be established, it's a mandatory thing. Site protection terminal fall back to distance protection mode. We cannot be sure, 100% sure, what timing source will be available. And what data channel will be available. Bad thing, because of money saving, often this data communication channel, fiber optics, goes the same road as our line. For in more, how to say, luxurious design, here it is set, it's OPGV, so-called. It's a protective cable on the top of the towers. Inside, it's a small plastic pipe, and here should be fiber optics. It's, how to say, more luxurious design. On cheaper designs, fiber optic channel, this fiber optic channel formed by cable attached between lower phase to make maintenance to lower safety requirements for maintenance. Or I saw designs that to prevent unauthorized access. Fiber optic cable is attached to lower phase. To keep it, on the other hand, to keep it under voltage to prevent unauthorized access. In such case, fall of line tower mean interruption of data channel. Bad news. Yeah. Itself, characteristic of such protection, nothing special. Operation I1 plus I2 just A1. Same chart as we saw for transformers. It approximates current sensor's error, and usually to avoid misoperation on inrush, it has protection from exponential component and also trigger for 5 omega t to prevent false operation due to current transformer saturation. So it has restricted characteristics. If M5 arrive, protection goes to not full disabling, but switch to restricted operation characteristic. So here key moment is in data exchange. Also, what else? I need to, these protection are, of course, most expensive, but they, if exchange works, they offer us a best performance. They are faster, they 100% selective, so it's high end of line protection. Another area where we will see pivot wire or differential protection, or one more. First, we saw so-called longitude protection. One of the protections I really hate is this one. It's so-called cross protection of line. Cross protection of parallel line operates from current difference between two parallel lines. Why I hate it? Because it's a trap for human mistake. For example, we need to service this line. What we do? We disconnect the switch. Instantly, operation current of the second line trips this relay. So, though this protection should be disabled before line is disconnected. I don't like this protection. Cross differential protection. When longitude is works very well, this cross differential, more disconnection from human mistakes and really needed. I don't like it. Yeah, what I wanted to speak, generators. Generators are very expensive. Fault in generator can cause mammoth amount of money. So, generators are mandatory. It's really mandatory for large generators to get both. This is longitude differential protection for high end. A, B, C, both longitude and cross section protections are installed. It's a mandatory. Both longitude and those would operate on difference between branches. High gigawatt class generators definitely will have multiple parallel branches in its tighter winding. So each branch should be equipped with longitude differential protection, and current between branches should be compared. Works instantly. All characteristic standard approximation of current transformers error. Really around multi-megawatt class generator, you will have around 12 parallel pilot wire or differential protection branches. Should be stabilized for error, and one more thing, they should, good practice, to have 50 Hz filters to make them immune to 100 Hz component. It can be caused by transients. And safeguard restricted characteristic from 5th or 5th plus 7 harmonic. It's necessary to prevent false operation during transients. What else? For generators, they are expensive. Oxford protection is needed. Some companies allow to operate for some time with Oxford because generators are they operate in isolated neutral mode. Some companies do disconnect instantly, but Oxford protection is needed. First, if this is neutral power generator, is of course a neutral displacement something like this will be structure of our schematic. Generator, delta star transformer outside. Neutral displacement relay in normal mode without earth fault, there will be 0. In case of earth fault, here will be what? 100 volts. But earth fault can occur here, but it also can occur here at the neutral. It is not a giant problem until second earth fault occurs somewhere. If we have pair of earth fault, we are in trouble. In this case, 1 to 1, maybe second earth fault here. It's a guaranteed disaster. So we need earth fault, very specific earth fault protection, able to detect earth fault near neutral. Good practice is to equip our generators with third harmonic differential protection. This protection, how it works? Grounding transformer, from here it goes to band pass filter 150 Hertz. This is voltage 1. From here voltage transformer A, voltage transformer B, voltage transformer C. Phase voltage are taken to some function, and from some function again to band pass for 150 Hertz. This will be U neutral, U line. Two voltages of 150 Hertz from neutral and from line goes to voltage comparison characteristic function. What's the idea? See, generator voltage contains third harmonic. No one bothers about it, because in the schematic of isolated neutral, third harmonic current cannot circulate in transformer winding because it's delta connected. So there will be no voltage disturbance at customer. But our long winding we can consider EMF, capacitance, EMF, capacitance, and so on. So we will get picture like this. It's at 150 Hertz. Third harmonic longitude. If we compare them, delta, on the healthy winding, delta is 0. If, for example, here earth fault happens, this chart shifts like this. And delta will be not 0. Delta will be full third harmonic voltage of our winding. This protection has a sensitivity chart like this. It's less sensitive in the middle and more sensitive at the ends of winding. Combined with neutral displacement relay, you will get full protection for your generator. It's a protection from internal earth fault. The only moment it has one, how to say, underwater stall. Balance 150 Hertz from the full line, on neutral 150 Hertz. Balance between them, we need a balancing, so regulated factor, delta U. This chart is interesting. Here, operation characteristic should be something like this, where here delta U 150 Hertz, and here absolute value of 50 Hertz unit, because of generator nonlinearity. Also, short time delay should be introduced. But there is one moment why I'm leaving space here. Because if we balance our protection, capacities are not uniform. We need to balance our protection. If we balance our protection when generator is connected to network, this balance will be disrupted at the moment generator is disconnected from the network. So first, if there is a switch between generator and block transformer, disconnected state of the switch should disable protection. And that's not all. Problem is, most for hydro generators, they can operate in quite wide range of frequency, and remaining resistant magnetization of generator rotor can produce some voltage at some frequency. So, to prevent misoperations, line at 50 Hertz, this protection should be disabled until output generator voltage at 50 Hertz is at last 0.9, or it will misoperate. Because under-excited, even if there is no exciting current, generator will produce some voltage. There will be something, some noise. And this can be treated as a difference in third harmonic voltages, as a disbalance. So to prevent this, safeguard should be placed. This protection should be disabled until output voltage of generator reaches at last 80%. And would be better to check not simple voltage. Cheaper model use line voltage. More expensive models use voltage of direct sequence. Or it will operate falsely. Also, in some hydro power plant designs, at output of generators, capacitors are placed. they reduce over voltage, and these capacitors are used to balance capacitance along the power, this power path. Disconnection of these capacitors causes relay to misoperate. Good idea is to control third harmonics current. Take a current from current sensors and check it for minimum. But this transformer should be before capacitor. This will check current of these balancing capacitors. What else? What else? What else? What else? Sorry. What else? What else? What else? Yeah. To prevent misoperation in transients, because it can be done, use good practice for such protection, set time delays about 1 second. To prevent misoperation at the moment when generator is excited. So where is today? We have 9th of December, yeah? 9th of December. Where is my attendance chart? Please, come on. Oh. Nothing to import. Okay, nothing, so nothing. Yes, attendance chart field.